Our goal here is to prove the alternate interior angle theorem. So let's review what that theorem is all about here. And remember that we stated this thing as a biconditional statement. This is alternate exterior. Here we go, alternate interior angle theorem. Basically, the setup is this, is that when we have parallel lines, the alternate interior angle theorem is going to declare that the alternate interior angles are congruent, like 4 and 5 in the picture. Conversely, if the alternate interior angles are congruent, like 4 is congruent to 5 in this picture, then we can conclude that the two lines are parallel. It's a biconditional statement. And anytime that you prove a biconditional statement, you actually have to do two proofs. You have to do it one direction, and then you have to do it in the converse direction, which is why when you look at this proof here, too far. Okay, when you look at this proof, we have two sets of given and proofs, because we're going to prove first, or start first with the parallel lines, and then prove that the alternate interior angles here are congruent. And then on the converse side of things, we're going to assume that the alternate interior angles are congruent, and then prove that the lines are parallel. Okay, now remember that whenever you go to prove a theorem, and in this one it's the alternate interior angle theorem, you cannot use this theorem in its own proof, because that would be circular logic. Instead, what you have to do is tie it back to the postulate that it's associated to. And the postulate that this thing is associated to is the corresponding angles postulate. So this thing is going to be proved based on the corresponding angles postulate. Okay, so here's kind of the setup. You want to do a little bit of brainstorming before you dive into your statements and reasons. Our goal is, on the first proof, to show that 3 is congruent to 6. So I want to pick some corresponding angles that match up with one of those angles. For example, I don't want to use 1 and 5. Yes, those are corresponding angles, and we'd be able to say that they're congruent, but the reason why I don't want to use it is because they're not necessarily associated with 3 and 6. Now, you could make it work, but it would be a longer proof. You'd have to go through more steps, and in particular, you'd have to show that these things are supplementary and those things are supplementary, and then you could get that 3 is congruent to 6, but there is a shorter way of doing it. What you do basically is that you try to find some angles that are corresponding to the ones that you're trying to show are congruent. For example, what is corresponding to 3? It's 7. Or alternatively, what's corresponding to 6? That's going to be 2 up here. And I can make either one of these things work. So let's take a look here. I am going to get for free, by the corresponding angles postulate, since the lines are parallel, that either angle 3 is congruent to angle 7, or angle 2 is congruent to angle 6. And like I said, we can make either one of them work. So let's just try the first one and see if we can carve a pathway that's going to be able to show us that angle 3 is congruent to angle 6 here. Okay, so since the lines are parallel, I'm going to get one of these sets of angles. Let's start with this guy here. Okay, so 3 is congruent to 7, but I'm trying to get 3 congruent to 6. 7 is going to be kind of like the middleman. 7 is also congruent to, if you notice, angle 6. Why is that? Well, look at where these things are. These two things are vertical angles, and we know that vertical angles are supposed to be congruent. So I'm going to make some sort of note about that. These are vertical angles, which are congruent. And that's going to be the linkage that I need to tie it to 3 and 6. So this means that even though I can make 2 and 6 work, I don't need to, because the 3 and the 7, the first one that I tried, worked out just fine. So here is kind of the setup here. I'm starting with my lines being parallel to each other. I'm going to get for free, by the corresponding angles postulate, which I just erased for the second time. The corresponding angles postulate is going to give me that 3 is congruent to 7. I know that 7 is congruent to 6 because vertical angles are congruent. And then finally, I should be able to tie that to 3 and 6 being congruent. And basically, that's the transitive property. So again, I want to highlight what I just modeled for you. And that's this process here. This one's not the proof. It's thinking through the proof. It's doing the brainstorming how you're supposed to link those ideas together before you sit down and actually write down your statements and your reasons, which we're going to do right now. Okay, so statements and reasons. First one, we will start with, of course, our given information that our two lines L and M are parallel to each other, which is given. And then since the lines are parallel, the parallel postulate, no, not the parallel postulate, what am I talking about? The corresponding angles postulate is applicable. I get to use a set of congruent corresponding angles, and the ones that we chose were 3 and 7. So on number 2, I'm going to say that angle 3 is congruent to angle 7, and that is the corresponding angles postulate. And if you don't remember the name of the thing, it's perfectly acceptable for you to just say that corresponding angles are congruent. Okay, and then what's 7 congruent to? 7 is congruent to 6 because vertical angles are congruent. So on number 3, angle 7 is congruent to angle 6. And I can either write the name of the theorem, which is the vertical angle congruence theorem, or I can simply say that vertical angles are congruent. Right, and I'm nearly done here. 3 is congruent to 7. 7 is congruent to 6. So we're going to cut out the middleman and go from 3 being congruent to 6, and that's the transitive property. So number 4 here, angle 3 is congruent to angle 6. This is not substitution. You can't have substitution with shapes. Instead, we have the transitive POC, property of congruence. Transitive POC. And there you have it. There's the proof, at least of 1/2 of the alternate interior angles theorem. There we go. Now we just have to prove it the other way. But you know what? This proof is way easier than this one. And the reason why is because what you'll find for converses is that more or less it's this process backwards. Okay, so here, let me dial this thing back. Let me rewind this process. Delete. Okay, now we're not going to get that these lines are parallel, right? We're starting with angle 3 being congruent to angle 6. That's what we get for free. And then we're trying to prove that the lines are parallel. In order to get the lines parallel, we have to show that a set of corresponding angles are congruent, and then the corresponding angles postulate would declare that those lines are parallel. So just like we did before, we just need to find a set of angles that are congruent to either 3 or to 6. And the one that I'm going to use is the one that we used before. Again, it's this guy that's right there with the vertical angles being congruent to each other. So if I mark that in the picture, we can see the path that we're going to carve through this. 3 is congruent to 6, 6 is congruent to 7, which is going to leave us with 3 being congruent to 7 by transitive property once again. And since those are congruent corresponding angles, the lines must be parallel. All right, so let's write that up formally. Statements and reasons. Okay, this time we're starting with the two angles being congruent to each other, which is angle 3 being congruent to angle 6. And that's given. And we were able to link angle 6 to angle 7 because vertical angles are congruent, sort of like what we did on the first proof. Angle 6 is congruent to angle 7 because vertical angles are congruent. That looks fabulous. Here, let me clean it up just a little bit. There, that's better. Anyway, number 3. Now, we're going to cut out the middleman. This time the middleman is 6. 3 is congruent to 6. 6 is congruent to 7. Therefore, 3 is congruent to 7. Angle 3 is congruent to angle 7. It is the transitive property, once again, transitive POC, because we're dealing with congruent angles. And 3 and 7, what kind of angles are those? 3 and 7 are corresponding angles, and the corresponding angles postulate, the criteria is met to establish that line L and M are parallel to each other. So on number 4 here, we can finally say that L is parallel to M, since the corresponding angles are congruent, which I will write as corresponding angles postulate. Now, the stuff that's in the book is going to list this as the converse of the corresponding angles postulate, which we're not going to make a difference between because we combined the corresponding angles postulate together with this converse to make a biconditional statement, which contains both of them. So if you just list it out as the corresponding angles postulate, you're perfectly safe. Now, this was an example of proving a theorem. And when we prove that theorem, remember that you cannot use that theorem in its own proof. You want to tie it back to some simpler ideas, some free ideas, some postulates. And in this case, it's tied back to the corresponding angles postulate. In the next one, what you're going to do is you're going to prove a situation in which you use whatever's most appropriate for that diagram, for that problem. You're not limited to just the corresponding angles or just the alternate interior angles. You use whatever's appropriate.